Just, yeah, I see my own screen in your. It's good. Okay. So hi again, everyone. I'm just going to talk to you about this notebook that I made for neutrinos. I should say that actually, I guess if you did Igor's notebook from yesterday already, then this should all feel rather familiar to you, because actually the things that we're doing with ZTF data are mostly the same. In general, we're trying to basically take the data and reduce the volume and identify the likely transients and get rid of all the things that aren't transients, as I showed in my slide earlier. And that's exactly what this notebook is supposed to do, and also what many other people in ZTF are trying to do as well. So, right. The first thing to say about the notebook on a kind of a high level is that the neutrino data, so this notebook uses ZTF data. And so you need to just go and download the ZTF data yourself. It's in, there are instructions in the notebook for how to do it. So you should just go to the Dropbox link that's here and download the data. It's called ZTF_summer_school_neutrinos.pickle. A pickle file is like this, this Python way of sort of storing data. So you should just download that, and you should put it in lecture/03/data, and then you can use the notebooks afterwards. And the code will tell you, like it will give you a warning if it couldn't find the data. So that's the important thing to know at the beginning. So okay, going on to like what you're actually going to do in the notebook. So basically, when we do neutrino follow-up, we have a localization provided by IceCube. And this notebook is going to let you do the follow-up of one neutrino yourself. So what I've done is I've gone to the particular neutrino. The neutrino has a localization by IceCube that's reported as a rectangle. And so I went into the ZTF data and I basically cut out the rectangle and took everything that was detected in the rectangle in the 24 hours after the neutrino was detected. And I just made the cut because otherwise the data volume is too big to share with you. But all you need to do basically is try and analyze the data from there. So this is, other than that one or two cuts, this is the full unvarnished alert stream. So everything that you get, a random representative sample of what you get out of ZTF data. The data itself was retrieved from Ample. So Ample is this broker slash database slash general all-purpose one-stop shop data management place for ZTF and also for LSST. So it's basically the software framework that is designed to analyze high volumes of astronomy data. And if you're interested in how this works, there's a link to the archive paper in the notebook. So anyway, you come through, you load up the ZTF data. This just takes a second. And if you open the ZTF data, you'll see that it contains 1,390 sources. And it's just literally a dictionary. So the dictionary has 1,390 keys. The key for each source is the name of the source. So you can just scroll down and see there's many, 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 many names here. And the idea is to basically work on this data and filter through these many, many sources to try and find the interesting ones. So let's try and visualize the data. So the first thing is just if you loop over the data and you plot the positions of each of the sources. So the sources are in a deck. And what you'll find is something that looks like this. This is a rectangle, and that's what you want because the neutrino localization was originally a rectangle. And so I cut out a rectangle of data. It is extremely reassuring to find a rectangle at the end. So the data that comes out of Ample is in kind of a similar format to what you worked in before. So we can look at an individual source. So I just picked one that I liked. And so you can access the data that's shown here in block 8. So if you just print candidate, has all the information, and you can see you have all of these ZTF fields. I think Igor's notebook also showed you that you can look these up. If you just Google ZTF Avro schema, there is a GitHub page that has all of this information for like what all of these mysterious words actually, what is C ratio, what is A image, what is N neg, what is RB, etc. So basically, this is the data you have to work with at the beginning. And right, then the question is, how do you proceed? So the first thing the notebook does, again, you code up something to plot ZTF light curves so that you can actually dig into the history. ZTF light curves have this thing called previous candidates, where it's like the last 30 days of detection. Actually, AMPL does something more clever. So AMPL will go and get the full history and aggregate it for you. So that's what you've got here. I think it's somewhat similar to the Kowalski notebook that you might have been working on from Igor. So basically, you just look in the previous candidates and it tells you all the times that an object was detected. And then you have the most recent candidate, and you should just add those two things together. And then you have the full history, including the most recent detection. So I just wrote up a little script to plot the data. So you just put an alert in, you add in the recent detection to all the old ones. You plot it by color. So ZTF has 3 filters: G band, R band, and I band. And these are color coded: G for green, R for red, and then I is infrared that doesn't have a visible color, but we assign that orange conventionally. And then, so you just plot the data. The ZTF data has 2 things. It has actual detections. That's where mag PSF is in the data point, or it also has non-detections, and that's when mag PSF is not in the data point. So anyway, this script, you basically just stick in ZTF data and it plots it for you like this. It also plots the neutrino in question, the arrival time here, the dotted blue line, so you can always have a look and see where the neutrino came relative to the rest of the data. So let's look at this source a little more. What can we learn about this source? So this is not likely to be a variable source. This looks like a transient because it doesn't have a lot of past detections or future detections. And that tells you it's probably a transient. You can also look at the color. So if you look at the G minus R color, the difference between G and R, at the beginning, it starts off blue because G is higher than R. And then over time, it flips and R becomes brighter than G. So that means it goes from a blue transient to red transient. And since these transients or these astrophysical sources are usually emitting like black bodies, the shape of the black body spectrum depends on the temperature. So this is a real physical thing that you're learning about here. What you're seeing is an object that is cooling, and as something cools, the black body temperature moves to red from blue. So if you know that you have a transient that's evolving over this time period, it's probably a supernova. At least that would be my first guess. But my guess is not really, it's not good enough. What you should really do is take a spectrum. You should take an optical spectrum of this source in order to classify it. And that's the main point of the ZTF neutrino follow-up program, and this notebook in particular, is that I would love to take a spectrum of 1,400 objects every time I do neutrino follow-up. But unfortunately, no person in the world is insane enough to give me that much telescope time. So actually, we only have resources to get spectra for maybe 1, 2, 3, 4 objects. That's it. So we need to identify very efficiently which ones are the most compelling, and then go and get a spectrum of those sources to classify them. So how do you go about doing this? Well, as you may have heard already, our ZTF data contains the following categories of objects: basically image artifacts, solar system objects, stars, active galactic nuclei, or other variables, I should say, and transients. So basically the aim for you is to try and separate these sources into 5 categories. And there's not like one real answer that's correct, but there's several similar ways of doing this. I mean, you might find this similar to what Igor was doing, or what maybe Tomas was doing, or anyone else. So it's just about like looking and trying to come up with something reasonable to do each of these steps. But again, it's not like if you pick a cut that's 0.6, it's correct, and if it's 0.5, it's not correct. There's always a bit of leeway, and there's always many right answers. It's just there's a common approach to the problem, but your exact solution, it should be your own. So the first thing you should look for are image artifacts, because there will be a lot of these. These are subtraction artifacts. So the best way to identify them is by eye. But it would be insane for me to tell you to scroll through 1,400 images and try and pick which ones look real and which ones don't. So instead, we use an approximation, and that's the yeah, the ZTF human eye approximation in the form of a neural network, which looks at the image and tells you whether it's likely to be real or bogus. That's how we define it. So real is real and bogus is like a subtraction artifact. So to filter out image artifacts, I suggest you make a histogram of the real bogus scores assigned to all the images. It's all in the data. So they have this DRB score, that's what it's known as. So if you scroll up and you see they have somewhere, where is it? DRB, right? So this particular one got a DRB of 0.99992, and that tells us it's very likely to be real, not bogus. So what I would suggest that you do is you should go and get all of the alerts and pull out the real bogus from every single alert and make a histogram and have a look at how it looks like. And what you hope to find is that there's like a clear separation between real and bogus. And you should just look at this distribution and try and decide where you think a cut might be reasonable, where you have a lot of one group and not a lot of the other group. So you want to look for somewhere where you kind of have a minima, and then you can separate the two groups. Then you move on to solar system objects. Solar system objects are objects in our solar system, obviously, and that makes them somewhat distinct because over the course of a night or over a normal human amount of time, like 20 minutes, half an hour, they actually move. So what you should do is you should look through all the objects and you should require that each object was detected twice, because ZTF assigns a name based on a position. So if something is detected in the same position more than once, and if those two detections are separated by at least 15 minutes, then you are unlikely to find a lot of solar system objects. And there's a little subtlety here, which is that you can't just go and look in the previous candidates bit of the alert and say, oh, well, I'm going to just look at the len of that and say, oh, there's 3 entries, therefore it was detected 3 times. Because the previous candidates in ZTF has both detections and non-detections. And so you have to specifically make sure to look only at detections. Then you go on to stars. So stars are usually identified by morphology. There is the Pan-STARRS survey, which is deeper than ZTF and which has a catalog of 1 billion sources. And there's been this machine learning effort to classify all of them based on their morphology to decide whether they look more like a star or more like a galaxy. So what you should do is you should, similar to real bogus, you should try and make a histogram of the star SG scores, the star galaxy scores for all of your sources. Each source has 3 matches, the 3 closest matches, but I suggest for convenience, you should just look at SG score 1 and only consider the closest match. The alerts also have the distance from the source itself to the star. That's dist PSNR, distance to Pan-STARRS 1, 2, and 3. And again, you should just look at distance Pan-STARRS 1. So you should make a histogram of SG score 1s. You should try and decide somewhere that you think looks reasonable to make a cut. And remember, in this case, a high SG score means a star. So you want a high real bogus score, but you want a low SG score. And then you should make a cut, and you should have some radius around the position of the star. And you can do 3 arcseconds, 4, 5, or whatever. You can play around with this a bit, but you should basically have you should have a maximum SG score and a minimum radius from the source to the Pan-STARRS object. Then we get to the bit more like gray area one, which is active galactic nuclei. So that's a lot of what you have left. The thing is that unlike transients, which go up and down, AGN evolves slowly, and sometimes they go up and down and up and down and up and down. So at this point, if you've done things well, you should have maybe only like a few dozen candidates. So at this point, I had something like 50 left. And at this point, I'd really recommend that you just start going by eye, because it's really the best method. I think it's even the method I use most of the time. It's you can think that you could do it by an algorithm. It would probably be possible. It would take you a long time, and I think it still wouldn't be as good as a human eye. So my general rule of thumb is that I'm trying to distinguish between what's a transient and what's an AGN or possibly a variable star. And basically, I'm interested in transients because I need to classify them, and I'm not interested in the other things. So I want to know if something is a probable transient. So if it just goes up and down like our supernova, then it's probably a transient. If something is detected just a couple of times, then I would say it's a possible transient. I'm less confident, but it could well be a transient still. If something is detected in 2 batches with a gap, so sorry, let me just go one by one and show you the illustration. So this is a probable transient. This would be a possible transient. It's detected just twice, and yeah, it looks compelling to me, but also there's no history, and you would be much more confident it was a transient if you got a lot of extra detections. Then you have maybe what's more likely to be a probable AGN, something that looks like this, like something is detected, and then it's not detected for like, I don't know, 50, 100, 200 days, and it's detected again at the same level, and the level is very faint. This tells you it's probably a variable object, most likely an AGN. And yeah, the reason is just that like astrophysical transients evolve quickly. They don't wait around for 100 days. They would have to go up and down. And, it's possible that that happened, or that there are upper limits here, so that makes it unlikely. And then the other thing is you can look at things that have really slow light curves, like this. This is over hundreds and hundreds of days, or things that vary a lot. And this is almost certainly AGN. So what I recommend that you do is you go through your 50 candidates by hand, and you just literally make a dictionary, and you say, I think this is this and this is that. That would be my recommendation. You can always look things up. You can look at how nuclear something is. There are lots of things you can do, but I think just going by eye really will get you like 95% of the way there. So there's a bit of instructions about how to code it up, but basically what I want you to do is take these 1,390 sources and then try and work out, so basically my task to you is I'm going to give you 3 optical spectra that you can take. So I want you to go through all these sources and try and identify which ones would you choose, which ones do you think are probably real transients that you'd like to classify. And that's the basic idea. So I will be obviously available on Slack, or I don't know, Michael, how are you doing this on Zoom? If people have questions, do they join Zoom, or do I just hang around on Slack? But yeah, good luck, have fun, and yeah, I look forward to seeing what you'll come back with.
Yeah, so yeah, typically we've just been interacting on Slack. So huge thank you, Robert. Yeah, so as before, so we'll be working for another 40 odd minutes to get rolling. And then at least around here, we'll take a break and come back at 2 to, I mean, this is going to take into the afternoon, of course. But otherwise, yeah, thanks everyone, and see you soon.